Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause, and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1, rewrite the following as one iterated integral by changing the order of integration. So currently we have 2 integrals, and we want to find 1. One integral to rule them all. One integral to find them. One integral to bring them all. And in the light of multivariable calculus, bind them. Right? Yep, exactly. That's what we're going to do. So where do we begin? Well, let's start by understanding our regions. So when we write down an integral, we're actually storing information about what's going on. So the inner part matches with the inner D term, the outer part, the outer one. So this tells us, if we read the outer part, that negative 14 less than or equal to y, less than or equal to 2. There we go. That's the right order. Bottom to top, low to high, and minus square root 11 minus y, less than or equal to x, less than or equal to y plus 4 over 2. Now, the other integral. Okay, that says what? Well, again, we do our matching. And what do we see? For the outer layer, it tells us about y. So y here goes from 2 up to 11. And x goes from minus square root 11 minus y, less than or equal, that's supposed to be a y there, less than or equal to x, less than or equal to positive square root 11 minus y. All right, now, I recommend starting with the curves. We know the outer layer goes number to number, the inner curve to curve. So let's talk about these curves. And we have x equals minus square root 11 minus y, and x equals y plus 4 over 2. And here, x equals minus square root 11 minus y, x equals positive square root 11 minus y. Because we're switching x to y, we want to rewrite these. So not x as function of y, but y as function of x. All right, so let's solve for y. And one thing that's good is get rid of the square root. So we square both sides, and we get x squared equals 11 minus y, or y equals 11 minus x squared. Here we can multiply by 2. 2x equals y plus 4, or y equals 2x minus 4. All right. We actually did this one, so we can just go ahead and write it down. 11 minus x squared. And here, if you notice, the only difference is the minus becomes a plus. But when you square it, it doesn't matter. So it's still 11 minus x squared. Like, okay. Now we have some ideas. We have a sense of what's going on. So we really have 2 curves. This 11 minus x squared and this 2x minus 4. So let's see. Let's start with 11 minus x squared. Well, that's not so bad. That's a parabola. It's been turned upside down, that's the minus, and moved up by 11. That's the 11. So we have this parabola going down. So here's our y equals 11 minus x squared. Y equals 2x minus 4.
Okay, well, that's a line and has a slope of 2, y-intercept of -4. So we can just do a quick sketch and say, okay, this is y equals 2x minus 4. Now, quick question. Where do things intersect? All right, now we can probably do one of two things. We'll do both. One thing is we can say, well, we have the functions. Intersection is when they equal. So we can take 2x minus 4 and set that equal to 11 minus x squared. And if we do that, we can move terms across. X squared plus 2x minus 15 equals 0, which becomes, if we factor, and it'll probably factor nicely because we have nice people who write these problems. So that's x plus 5, x minus 3. Check it out. X squared, good. Minus 3x plus 5x, 2x, and minus 15. All right, which tells us the intersections are at -5 and +3. So here, 3, and here, -5. Now, that tells us where the x values are, and we could write down the answer now, but I want to point out something. Let's talk about y values. And, well, in particular, if you plug -5 into either curve, doesn't matter, let's plug it here. 2 times -5 minus 4 will give us minus 14. Now, have we seen minus 14 somewhere before? It's right there. If you plug 3 in, 2 times 3 is 6 minus 4. What does that give us? 2. Right? And by the way, where's the top of this? 11. And now we can see why they had to split where they split. From -14 to 2, if we're going horizontal, then what do? Well, you have to go from the left side of the parabola over to the line. So that's why you have -14 to 2, left side of parabola over to line. But at 2, for y equals 2, the behavior changes. And when I say the behavior changes, the bounding line changes. So now we're going from left side of parabola to right side of parabola, and that's from 2 up to 11. So 2 to 11, left side to right side. So how do we now get our final answer? Well, it's actually all laid out for us. And we say, okay, what's going to happen? Well, we're going to integrate, and we know it's one integral. So fxy, and we're changing the order of integration, dy dx. So let's talk about what's going on. We'll start with the outer layer. Where does x run between? Low value of x to high value of x. The answer is we start at -5 and we go to +3. So that's -5 to 3. Now, where does the y go from? Well, for a given x, we're going to run from the line to the parabola. So low to high, which means 2x minus 4 to 11 minus x squared. And that's our y bounds. And we're done. We can't integrate this. We don't know the function. It's about setting it up. And a lot of this part of the course really comes down to, can you set it up? Can you see the geometry? Because if you can see the geometry, then you understand what's happening. And once you understand that, you can make wonderful progress. All right. Well, we're going to get to do this a lot more, so let's keep going. Number 2, evaluate this integral. We go from 0 to pi over 4, x to pi over 4, secant squared of y over y, dy dx. And you're looking at this like saying, hopeless, hopeless, right? What's the integral of secant squared over y over y? Actually, that's pretty accurate to say hopeless, right? You're not going to be able to integrate this with respect to y. And so it's like, okay, I guess we're done. But it's not just a one-dimensional integral. It's two-dimensional. You say, okay, look, I can't integrate this with respect to y. But I can integrate this with respect to x all day long because there's no x. So maybe instead of saying I'm faced with an impossible integral, let's change the order of integration and at least make a dent. And maybe it's a big enough dent we can succeed. So this happens a lot. This is one of the favorite types of problems people like to write for multivariable calculus. They say, hey, here's this crazy integral. And then it's like, oh, but if you change the order of integration, not so crazy. So let's start by saying, let's look at our region. All right, so we do our pairing up. And we say, what's going on? Well, the outer layer, that's associated with the x. And so we're told x goes from 0 to pi over 4. The inner layer, that's associated with y. And that says that x less than or equal to y less than or equal to pi over 4. And now we say, okay, we think we can get a handle on this one. If we sketch our curves, there's really just two curves, right? The x equals y curve and the y equals pi over 4 curve. Now, x equals y is the same as y equals x. And y equals pi over 4, that looks like this line. Y equals pi over 4. And where are we going from? Well, we're going from x equals 0, which is over here, to x equals pi over 4. Now, which part are we actually integrating? Be careful, right? Because sometimes you might say, oh, maybe there's two triangles here. Is it this one or is it that one? And it makes a difference, right? So what do? Well, here's how you can figure it out if you're ever in doubt. You say, okay, pick an x somewhere in between. So I'm between 0 and pi over 4. You say, okay, where does y start? It starts on the line y equals x and runs up to the line pi over 4. You're like, okay, so I'm going in between these two curves. And so it's this triangle here. And I'll shade it in. All right, so this is our triangle. Now, what are we going to do? Well, we're going to switch order of integration, which really comes down to we're going to switch the way we slice. So here, dy dx, that's the blue one. And I'll make a little note here. This is our dy dx slicing. And now for the red, which is horizontal, that's our other option. And that's our dx dy slicing. So we say, okay, great, great, looking good. So what do we need? Well, we need to re-describe our region. And so we say, all right, well, let's talk about y. Where does y go from, right? Because if y is going to be our outer layer, and it is, so I'm going to copy this down here, dx dy. So the y is the outer part. Where does y go between? Well, what's the smallest value of y to what's the largest value of y in our picture? So we see the smallest value is 0, and the largest is pi over 4. All right, so that's our outer layer. Now, where does x go from? Well, we go from left to right, small to big. That's always the process, small to big. Okay, so we start at 0, and we go to this line, y equals x. So 0 less than or equal to x, less than or equal to y. So 0 to y. Now, by the way, this already looks more attractive. If nothing else, you'll notice this has 2 zeros. This only has 1. The more zeros, usually the better. Not always, but usually. And so, okay, good. And now the moment we've been waiting for. We can finally integrate. Because at this point, this is like a constant with respect to x. Because it's a constant with respect to x. So that's a good reason why it's like that. So what do we get? Well, this becomes the integral 0 to pi over 4 secant squared y over y times x, evaluate x equals 0 to x equals y. Right? Because these are x bounds. Now, when you plug in 0, you get 0. That's nice. When you plug in y, what do you get? Well, you get 0 to pi over 4 secant squared y over y times y. But if you have two y's, they cancel out. Pew, pew. You don't have to make the pew sound when you're doing the problem, but it feels good, doesn't it? Yeah, of course it does. All right, now we're left with secant squared. Do we know the integral of secant squared? Yes. It's tangent. Nice. So tangent from 0, I'm going to specify y equals 0, to pi over 4. All right, so that becomes tangent of pi over 4, subtract tangent of 0, and well, tangent of pi over 4 is 1, and tangent of 0 is 0, and so we get 1. It is the 1. Ah, beautiful, beautiful, lovely. And all right, there you go. There you go. Isn't that amazing? Now, you might say, hey, isn't there a small technical issue? Like, there's this little corner here. Isn't this blowing up? Kind of like improper? Yeah, okay, ignore that. We're not doing that. We're just going to let it ride. And because, well, life is good. Life is wonderful. All right, well, lots more to do. Let's keep going. Number 3, evaluate. We have an integral, 0 to 2, x to the square root of 8 minus x squared, e to the negative x squared plus y squared, dy dx. And this makes us say, Now, you might say, well, what's wrong? You're not going to integrate that with respect to y. So you're like, hey, we just learned a trick. Change over integration, right? You're not going to integrate that with respect to x either. And then you're like, dang it. Well, what are we going to do? Well, we're going to look for clues, right? Because problems give us clues. And there's a big clue here. This is what? X squared plus y squared. Now, here's what happens. When we see x squared plus y squared, it triggers a thought. And so we have a little epiphany. And the thought is very simple. X squared plus y squared is r squared. So when we see that, we're like, ooh, polar. All right, so that's a clue. There's another clue. It's a little bit more subtle and not quite so obvious. But if you think about this piece, the bound, that one, what is that? What is that bound? We're going to see it in a second. But when you see something like square root of something minus x squared or square root of something minus y squared, that's a circle. So when you see a circle, and polar loves circles, or you see an x squared plus y squared, polar loves x squared plus y squared, you're like, switch to polar. So that's our plan. And now we have a plan. And that's good. We love it when a plan comes together. All right, so our plan. Switch to polar. Okay. Now, how do we do that? Well, we remember that there's always three things you have to take care of for every integral. What's the region? What's the function? And how are we breaking things up? Now, it doesn't matter which order we do it. We're going to have to address all three of those things. And then we just have to put it together at the end. I say just, but it's not trivial. So don't rush yourself. Let's start with this part because this is low-hanging fruit. When we talk about dy dx, this is doing a nice job for us. This is our little bit of area that we've chopped things up into. And in polar, this will introduce an r dr d theta. And by the way, the whole reason why this whole grand scheme is going to work for this case and things similar to it is this introduction of this r. This extra r, which seems so harmless, so innocuous, will turn out to be just the thing we need to make progress. All right, so that's the dy dx. That's how we handle that. Now, what about the function? Okay, so that's actually pretty straightforward. That's already in our sort of bubble. X squared plus y squared equals r squared. We have to rewrite this in terms of r and theta, but we're ready to go. Now, it's possible they have x's and y's, so don't forget there's these sort of other thoughts that might permeate. X equals r cosine and y equals r sine, but usually x squared plus y squared is your go-to. And that'll carry you through a large chunk of the way, if not all the way. Now, the real moment of truth. Let's start talking about our region, which means we need to get into our bounds. So, our region, 0 less than or equal to x less than or equal to 2. And we have that y goes from x up to square root 8 minus x squared. Okay, well, we should try to get some sketching going on here. Bit sketchy. And what can we do here? Well, we have some lines which are pretty clear, right? This curve at the bottom, this is the curve y equals x. So, great. Y equals x. No problem. This curve, y equals the square root of 8 minus x squared, a little bit more subtle. So let's take our time with it. So y equals the square root of 8 minus x squared. Square it. Y squared equals 8 minus x squared. Move things around. X squared plus y squared equals 8. And that's the circle I was talking about earlier. It's a circle centered at the origin of radius square root of 8. Okay, well, that's fine. And so we have this circle here. Now, think about what's going on. We're going from 0 to 2, and you might say, do these intersect? Well, let's just check. When you plug in x equals 2, you get 2. That's from y equals x. Here you get square root of 8 minus 4. That's square root of 4. That's 2. So they actually do intersect here at 2. So we'll go from 0 to 2 for x, and then for any x in between, we go from the bottom curve, which is x, to the top curve, which is the square root of 8 minus x squared. All right, well, which means if we add in some shading here, our region, it's a wedge of a circle. All right, so there's our picture. Now, we need to describe it. But we aren't describing it in terms of x and y. We're moving into polar. So we have to think about, okay, how do we describe this in terms of polar? Well, in polar, we're going to say we have some range for theta, and then we have range for r. So we need to say, where does theta go between, and where does r go between? Well, so remember, how does theta work? You start, everything goes back to the origin. In polar, it all goes back to where you come from, the origin, the center point. So think about theta, and that's our rotation. So when do we first hit our region? And the answer is where we miss until this angle, which corresponds to y equals x. That's pi force. Now we hit, and then we exit when we're here, right? Because as soon as we go past, we're no longer in our region. So what's this angle up here? Straight up the y-axis, pi halves. So theta goes from pi force to pi halves. Now, where does r go from? And remember, we always talk about in relation to the origin. So in dy dx, you slice, up and down or left and right. In polar, you slice from the origin out. So where do we start? We start at the origin and we go until we hit this circle. So we start at 0. And now what's the circle? Well, it's a circle which has radius square root of 8, or r equals square root of 8. And that's the bounds. That's the description of our region in terms of polar coordinates. So we're now ready to put all of this together. And what do we have? Well, we have that this integral is equal to integral r e to the minus r squared r dr d theta, theta pi over 4 to pi over 2, r 0 to square root of 8. Okay, now we're ready. Previously, this integral with respect to y or with respect to x, hopeless. And not because I don't think you're great. I think you're wonderful. It's just it can't be done with basic elementary functions. It's impossible. But that's where this extra arc comes in to save the day. We can do substitution. So that's our plan. We're going to let u equal r squared. And what does that give us? If we let u equal r squared, du is 2r dr. And I can use my fancy markers here. A half du is r dr. So what do we get? Well, updating, the outer layer has not changed. Still pi fourths to pi halves. The inner layer is about to change. It becomes e to the minus u, r dr, 1/2 du, and then there's still a d theta. And now our bounds. All right, these are our r bounds. We need to switch to u bounds. And we say, okay, well, if u equals r squared, r equals 0, 0 squared is 0. Up here, r is square root of 8, square root of 8 squared is 8. And there we go. And now, notice we've updated the bounds. We're never going to have to go back to r. What's the integral of 1/2 e to the minus u? Well, that would be minus 1/2 e to the minus u. Evaluate u equals 0 to u equals 8. And if we plug that in, we get minus 1/2 e to the minus 8 minus 1/2 e to the minus 0. E to the minus 0 also known as 1. So I'm just going to write this as 1/2 times 1 minus e to the minus 8. That's rearranged. That's what you get. And we say, hey, that's great. That's actually pretty easy to integrate with respect to theta because there's no theta. One of my favorite things to integrate, constants. I always do a really good job of integrating constants. All right, theta, evaluate from pi over 4 to pi over 2. And really, you just take pi over 2, subtract pi over 4 when you evaluate here. And we'll just make a note of this. This is going to become pi over 2 minus pi over 4, which is pi over 4. And so when we put it all together, we get our final answer of 1/2 times pi over 4, which makes this pi over 8 times 1 minus e to the minus 8. We're done. We got an answer. Woohoo! Is it a reasonable answer? I guess. I mean, it makes sense. The process works, right? It's just a matter of finding the right way to describe it. That's why we have more than one way to describe things. Because some things are hard in one description, but easier in the other, and vice versa. Use the right tool for the job, and things work well. So, in this case, it worked out pretty nice. Life is good. Life is wonderful. All right, let's keep moving along. Number 4, rewrite the integral. It's a triple integral. And there's no function, doesn't really matter, because our goal is to rewrite, not to actually integrate. dz, dx, dy, and there's various bounds. We're changing it to the order dx, dy, dz. Okay, this is going to be a minute, right? So I will say, I think this is one of the more challenging aspects of this part of the course, is rewriting integrals, and triple integrals are among the most fun. And we're going to have some fun. All right, so how do we do the process? Well, it's actually not so bad if you think about it. We say we're given an integral. Step 1, let's talk about our region in terms of bounds, right? How are we describing our region? The integral stores the description. So we start with the inner layer here if you want. Well, usually I start with the outer layer, but I'll start writing down the inner layer. So we have x goes from something to something. Y goes something to something. Oh, whoops. Sorry, I need to start. Y is the outer layer. Y goes from some place to some place. Then x, and then z. Okay, so z goes 0 up to this 3 minus 3/4 x minus 3/2 y. Next layer is the x layer, and that says x goes 0 up to 4 minus 2y, and then the last layer is the y layer, and y goes 0 up to 2. So this right here, that's the current, or if you like, the given description of our region. Now we want to figure out, what is this? What shape is this? And we say, okay, well, let's start building it up. So I like to build up. Now, I'll start here with the first two. And so we'll start in just 2 dimensions. We have x and y. And so we'll sketch, be a little bit sketchy here, x, y. And we're told y goes 0 to 2. So I'm just going to mark off here. I have a 0 and 2. So we're going in between there. Now, what about x? Well, what I'm told is that x goes 0 to 4 minus 2y. Now, x equals 0 has another name. It's called the y-axis. So that's x equals 0. X equals 4 minus 2y. Well, we can make some little computations here. We can say that's the same as 2y equals 4 minus x, or y is equal to 2 minus 1/2 x. So it's a line. It hits at 2, has a slope of negative 1/2, and didn't really prepare my picture well, but that's all right. And so where do we hit? Well, we're going to hit here at 4. You can figure that out by just saying, if x equals 4 minus 2y, at y equals 0, what's your x value? It's 4, right? 4 minus 0. Okay, and what's happening? Well, for any value of y between 0 and 2, we start at the low value and go to the high value. So that says our region, as of right now in the outer two parts, that's a triangle. And we'll shade it in just so we know. No doubts, no doubts, no doubts. Okay, so that's our outer two layers. Now I want to incorporate the third one. Going to move up to 3D. Okay, so we have our x, our y, and our z. Now we're going to mark some things. X, we're going to mark 4, because that's this point right here. Y, we'll mark 2. And this triangle comes down here. That's right there. That's that triangle. And so I'll still shade it the same color. All right. So here we have our triangle. Now we get to the last part, z. And we start saying, okay, what is z? Well, we have two surfaces, because you always go between two things, between two numbers, between two curves, between two surfaces, right? So we have two surfaces. One surface is at the bottom, z equals 0. So z equals 0 is the xy plane. And so in particular, that means we're actually coming from this triangle. That's the bottom. We're going to move up. Now we have this other part. Well, that's z equals 3 minus 3/4 x minus 3/2 y. And, okay, well, I'm not a big fan of fractions. So multiply through by 4. 4z equals 12 minus 3x minus 6y, or 3x plus 6y plus 4z equals 12. It's a plane. It's a plane. Now, how do you draw planes? Well, the good news is we don't have to draw very much. In fact, here's probably the best way to draw planes that I know of, especially if we have to rewrite the integral type problem. Where do you hit the axes? So, how do you figure that out? Well, if I want to know where I hit the x-axis, cover up y and z. You get 3x equals 12. You say, oh, I hit the x-axis at 4. Okay, so I'm going to mark that. Let's see, what's a good color that I haven't used yet? Oh, so many options. Okay, so I'm going to use green. We hit here at 4. Nice. You might say, ooh, coincidence? I don't think so. And they say, okay, where do we hit the y-axis? Okay, cover up x and z. 6y equals 12. That's at y equals 2. All right. Again, not a coincidence. Where do we hit the z-axis? Cover up x and y. 4z equals 12. And that's at z equals 3. Now, once you have 3 points, you can form a triangle, and that is in the plane. And in particular, we say aha, or ha ha ha, whatever the mood may strike us, we get that this is our plane. So here we have our 3x plus 6y plus 4z equals 12. Whew, good. Now, all of that is prelude. Let's start getting into the meat. We want to figure out our new bounds. So, I'm going to do this in sort of 2 parts. There's the innermost layer, and there's the outer 2 layers. Now, I'll start with the innermost layer. When we do our innermost layer, we say, what is our inner layer going to be? It's a dx. So we want to do something where we say, okay, dot, dot, dot. We have our integral dx, dot, dot, dot. Okay, so the inner layer. Now, the inner layer of a triple integral, this is the surfaces. Now, we have to think about what's going on. Here's the key. This dx tells you which direction you're moving, right? Because there's 3 ways. We could move in 1, 2, or 3 different ways. We are going to move in the x manner. In terms of our picture, when we talk about x, that means we're moving parallel to the x-axis. So here's the x direction. So as you think about your solid, and by the way, what is our solid? I should have paused. It's a tetrahedron. It's a tetrahedron where because what happens is you start on the base, go up to the top. So you have your corner here at the origin, and then you have your sort of 3 back faces, and then you have this slanted face. So now start thinking about it. As you move in the x direction, right? Previously we were moving in the the z direction. We were going up, down. Now we're coming this way. What do we hit? Well, the low value, which is in the back, we start on this back face. What is that back face? The back face, if we were to label it, would be x equals 0. We can actually label all of the faces here. So this bottom face, this is z equals 0. And this other face over here, this is y equals 0. So this back face is x equals 0. So we're going to go from 0. And now, when we move forward, what do we hit? We hit the slanted face. All right, so we get from x equals 0 this is our back. And this 3x plus 6y plus 4z equals 12, this is the front as we move. But I can't put 3x plus 6y plus 4z equals 12. Because when we talk about dx, we have x bounds. We need x equals. So we're going to move things across and solve for x. So 3x equals 12 minus 6y minus 4z, or x equals 4 minus 2y minus 4/3 z. And that's what goes up here. So 4 minus 2y minus 4/3 z. All right. Now, with that, we've got our inner layer. Now, we need to do our outer layer. And with the inner layer, we said, figure out what surfaces you move between. In the outer layer, you look down the axis and you see the shadow of the shape or the projection of the shape. There's a couple ways you can describe it. So notice how we went back and forth in x. So we're now going to look down the x-axis. It's like we imagine that we were over here standing and we said, let's look down and see what we see. So pull up the x-axis. What do you see? Well, you're going to see something in the y-z plane. Well, what shape? Well, you can mark it, right? It's a triangle. 2, 3, and it's that shape right there. All right, so here is our region. Now, as we work to set up our bounds, we say, okay, what we have for our outer layer is the following. We're going to have an integral. There's stuff in the middle, and then our outer layer is dy dz. So we need to start answering questions. Well, what can we say about z? Where does z go between? So low value of z to high value of z. So that's, in 2 dimensions, we're comfortable doing this. This is why I'm separating these. We say, oh, low value of z equals 0. High value, z equals 3. So 0 less than or equal to z less than or equal to 3. 0 to 3. Now, where does y go from? So pick a value for z. You say, all right, y goes low to high. What is the left-hand side? That is y equals 0. So you say, okay, 0 less than or equal to y. And now you say, but what's this curve? All right, that one you have to think about. And you probably can think about it in terms of, slope-intercept. And if you think about it that way, well, the slope, you go down 3 over 2, so minus 3 halves y, and the intercept is at plus 3. It's true. You can check, right? Plug in y equals 0, you get 3. And then if you plug in y equals 2, you get 0. All right. Well, if you multiply by negative 2/3, because why not, you'll get negative 2/3 times z is equal to y minus 2. Or if you add 2, you get y equals minus 2/3 z plus 2. All right. And there you go. So that's the other layer. We go from y equals 0 to y equals minus 2/3 z plus 2. And I should have said outer layers, not outer layer. And we say, okay, we've got the outer layers, we've got the inner layer. What do we do? Well, we just put them all together, and life is good. So we start with the outer layers, 0 to 3, 0, and that's a really badly written 2/3 there, but minus 2/3 z plus 2, integral 0, 4 minus 2y minus 4/3 z, and the function is just 1. And make sure you get the right order, dx, dy, dz. And there you go. Great, right? We can do this. And you're probably thinking, like, Steve can do this. No, you can do this. You are capable. I know it's not the most obvious thing, but be methodical. Say, okay, I've got my current integral, which gives me my current bounds described in a very particular way. And I say, okay, build up your picture and understand what you have. Now, starts thinking about, if I'm changing, I like to do sort of the inner layer and the outer layers a little bit differently. Inner layer, think about which direction you're integrating. We had started going z direction. Now we're switching to x direction. And to say, okay, well, what surfaces do we hit? You hit something in the back, you hit something in the front. Solve for the right variable. Boom, one layer down. Outer layer, look down the axis. And they say, okay, what shape do I see? Describe that, because 2 dimensions, we're a little bit better at 2 dimensions. And then put it all together, and life is good. Life is wonderful. All right, good. Well, let's get going. Number 5. The solid region bounded by the coordinate planes and the plane x plus 2y plus 3z equals 6 in the first octant has density delta xyz equals 2y. Find the mass of this solid. All right, this is going to be a ride. I should, in the interest of full disclosure before we begin, this will not be my first attempt at this problem. Because there's a lot of stuff going on here, and some of it's subtle and some of it's not. So let's enjoy the journey. Okay, so first off, we know we're after mass, and we know it's a 3D shape because it says solid. So for reference, we'll write down our generic formula. We have that mass is found by adding up, so triple integral because it's a solid, over our solid, our density dV. And we know our density explicitly, it's given to us, it's 2y. So this is going to be more than just a setup. It's the carrying out that's going to make it the most interesting. All right. Well, since it's a triple integral, we have choices to make. And namely, how do we integrate? We have x, y, z. We have to integrate each one of those. How do we pick? Before we answer that question, let's look at our region, because sometimes the way we integrate is determined by region, sometimes it's by function, sometimes it doesn't matter, and sometimes it does. Okay, so let's now, before we decide our order, let's talk about our shape. We're in the first octant. What does that mean? Well, if you're not familiar with the first octant, that's another way of saying x is greater than or equal to 0, y is greater than or equal to 0, and z is greater than or equal to 0. Okay, so everything's non-negative. All right, so we can start sketching. We will sketch. Here we have our x, y, z. We have some things. We have the coordinate planes. What are those? Well, the coordinate planes are just another way of saying things like xy plane, xz plane, and the yz plane. So we have the xy plane, that's z equals 0. The yz plane, that's x equals 0. The xz plane, that's y equals 0. So those are 3 of our planes. There's a 4th plane involved. And our 4th plane is this plane, x plus 2y plus 3z equals 6. Now, what's the right way to sketch it? Well, oftentimes I find the easiest way to sketch the x plus 2y plus 3z equals 6 is to look at where do you hit the axes. So if I want to know where I hit the x-axis, I cover up the y and the z, and it says x equals 6. So it's like, cool, let's do 6. If I want to know where I hit the y-axis, cover up the x and the z, 2y equals 6. So that says, oh, y should be at 3. And if I want to hit the z-axis, cover up x and y, 3z equals 6, and z equals 2. So we get that triangle. And that's the last piece. So we have 4 sides. This is a tetrahedron, tetra meaning 4. We have this back side. This is our x equals 0. we have this bottom side. This is our z equals 0. Oh, we have our, call it our left side. Here, that's our y equals 0. And even though it'll complicate the picture, we'll also sketch in our last one here, which is x plus 2y plus 3z equals 6. All right, now that we have our shape, we have our function, we can start thinking about the order of integration, triple integral. Well, there's nothing about the shape that really says one way is preferable to another way. There's sometimes your shape will have a certain way that the pieces are formed together, which says, well, if you choose one order of integration, you have two parts, but a different order makes it one part. Say, okay, do the order which makes one part. That's not the case here. So let's look at our function, 2y. Now, question, think about this for a second. We have to integrate with respect to x and y and z in some order. Would we like to integrate with respect to y early or later? Now, you might say, does it matter? Well, I'll tell you, having done the later, yes. So, as I said, I did it before, and I said, oh, what would it matter, right? But actually, here's the thing. It can make a difference. It won't make a difference in the final answer, but it makes a difference in the intermediate computation, and you want to make those as friendly as possible. So what's going on? Well, the longer you can delay the integration of what you're integrating, the longer it takes for things to build up. So if you integrate y early, you start building up those powers. And as you build up those powers, you're going to deal with, if you integrate y right away, you get to like a y squared. Then the next thing would be a cube, and then you end up with like a fourth, and then it's just like, bah. But if you can delay, you don't have that. Now, it's not to say that things won't build up, but you'll have a better control of what's happening. So if you're doing it by computer, let the computer worry about it. Computer doesn't mind. It loves computing. But if you're doing it by hand, delay as much as possible. So we're going to write down our plan. Delay integrating by y. Okay, so that tells us that when we write it down, our d, our last integral will be with respect to y. Now, the other two doesn't really matter so much, so I'll go dz, dz, dx, dy. Okay, so there's the plan. All right, now we have to set up our bounds. Okay, so that means we've got two parts. I like to break it into sort of like the inner bounds, the outer bounds. So for the inner bounds, or I should say inner bound, one singular, I'm going to think about surfaces. And as we look, we say, okay, what is the inner part going between? And in particular, we say, okay, look, z is our inner part, which means we are going to be moving in the z direction. So that's our z direction. So we imagine moving up and down in the z direction. We say, okay, where's the bottom to where's the top? So as we move up and down, what do we see? All right, so before I get too far along, I'm just going to set up so I have it for reference. Integrating, we know our function is 2y, dz, and we say, okay, so the bottom, that's z equals 0. The top, well, that's the other plane. That's our x plus 2y plus 3z equals 6. Now, here's the issue. Z equals 0, that's ready to go. We can write it in right now, so let's do it. Yeah, absolutely, we love it. That's not ready for us to write in, because our z bounds needs to be z equals. So we're going to do some rearranging. 3z equals 6 minus x minus 2y, or z equals 2 minus 1/3 x minus 2/3 y. I'm going to pause for a second and give you some advice. Learn to distinguish your z's and your 2's. Some people lose track. So I'm always very careful when I'm doing problems. I've gotten to the habit, I always put a little line through my z's, so that way I can read my own writing. That's such an important thing to be able to do. And I noticed I forgot to write down my x. Learn to read your own writing and learn to copy correctly. Okay, but yeah. So our upper bound, we get 2 minus 1/3 x minus 2/3 y. It's there's a lot to write there. All right, so that takes care of the inner layer. But we got the two outer layers. So now we got to do the outer bounds. So I'm going to look on those. And I'm going to think about looking down the axis. So I'm going to see that there's sort of a shadow, if you will. And I say, okay, so what's happening with my outer bounds? So look down the z-axis. And when we look down the z-axis, what are we going to see? So imagine you're up here. You're looking down the z-axis. You're going to see x and y. There's no more z. The z-axis is right here. What's the shape that you see? It's a triangle. And in fact, you can take advantage. Like, we know where we hit for x. We know where we hit for y. And so we have our triangle. Say, all right, beautiful, beautiful. Now, we're not done. We know the shape, but we got to describe it. And we got to describe it in the way that we're going to integrate. So our outer two layers, we have an integral, the inner stuff, and dx, dy. So we have to say, okay, let's start with the outside most. Where does y go from? So in other words, the lowest value of y to the highest value of y. Lowest value of y, 0. Highest value of y, 3. So we say that y goes from 0 to 3. All right, number to number, 0, 3. Now, fix a y value. So, okay, fixing a y value. Here's y value that I fixed between 0 and 3. And just say, where does your x go from? Low to high. What's your x value on the left? What's your x value on the right? On the left, x equals 0. So we're going to get that 0 less than or equal to x, less than or equal to the line. Now, for the line, it's probably easier to do slope-intercept form to start with. Down 3 over 6, slope is minus a half, and then y-intercept is 3. But the problem is this is a y equals. We need an x equals. Okay, so minus 2y equals x minus 6 multiplied through by negative 2, or x equals 6 minus 2y. Let's add 6. So that says, x goes from 0 all the way over to 6 minus 2y. And that is your other piece. All right. Good. Good. Okay, we've put in our work. It's been some work. Now, we're going to draw a dividing line, and we're going to write down our integral, and we're going to start chipping away at it. So, our mass is integral 0 to 3, integral 0 to 6 minus 2y, integral 0 to minus 1/3 x minus 2/3 y. Okay, 2y, that's the function, dz dx dy. And whoops, there we go. Okay, there we go. It's all there. Start integrating. All right, one layer at a time. Now let's just take it one layer at a time till we can get the integral that we need. Just one layer at a time. Integrating with respect to z, 2y is constant, right? That's our plan. Delay integrating with respect to y until the very end. So that gives us 2yz. Evaluate from z equals 0 to 2 minus 1/3 x minus 2/3 y. And I should put a z equals here. And that's dx dy. All right, so we're going to take 2y times this part, subtract 2y times 0. Hey, 2y times 0. Nice. That one we can do, right? So we have 0 to 3. We're still just rewriting here. 6 minus 2y. Then we'll distribute 2y times 2 makes 4y. 2y times minus 1/3 x minus 2/3 xy. And 2y times minus 2/3 y makes minus 4/3 y squared. All right. Good. Now, we've successfully finished integrating with respect to z, right? The hard part is the setup. Then the long part is actually carrying out the integral. We've got 3 layers. We finished one of them. 2 to go. All right. So we'll go to our next layer. Okay. So we're integrating with respect to x. This becomes integral 0 to 3 of 4xy minus 1/3 x squared y minus 4/3 xy squared. All right, so the 4y is the 2/3 y. No, everything's a constant other than the x. So that's why you have an x here. Add 1 to the power, divide. That's what happened to the 2. Then it's just all constants, so you just get an x. And we're going to plug in from x equals 0 to x equals 6 minus 2y. So, what does this become? Integral 0 to 3 of 4x, not 4x, I'm sorry, I'm replacing x. 4 times 6 minus 2y times y minus 1/3 6 minus 2y squared times y minus 4/3 6 minus 2y times y squared. Okay. All right. So now let's be patient and expand. I don't see any shortcut other than expand it out. You know, we're in our hunter-gatherer phase in a minute. So, okay, so 4 times 6 times y, 24y. 4 times minus 2y times y, minus 8y squared. Okay, that's the first term. We're going to make a little note here. 6 minus 2y, quantity squared, that's 36, a squared minus 2ab minus 24y plus b squared plus 4y squared. Okay, so we have minus 1/3 times 36 times y minus 12y. Minus 1/3 times minus 24y. That's going to be plus 8y times y plus 8y squared. Minus 1/3 times 4y squared times y. Minus 4/3 y cubed. Okay, then minus 4/3 times 6 times y squared. Okay, well, 3 goes into 6, so that's really going to be a minus 8. And don't forget the y squared. And here we're going to get 4 thirds times negative 2. Well, that's minus 4 thirds negative 2. That's a plus 8 thirds. And then we have a y and a y squared, y cubed. Okay, so that's what we have there. But we haven't done our hunter-gatherer, right? We got to start looking. So let's look for the y terms. We've got a 24y and a minus 12y, and that's it. So that leaves us with 12y. Okay, we have a minus 8y squared, a plus 8y squared, and a minus 8y squared. Well, the minus 8 and the plus 8 cancel. Minus 8y squared. All right, and then we have a minus 4 thirds y cubed, a plus 8 thirds y cubed, making it plus 4 thirds y cubed. All right, good. Whew. Hey, this looks like an integral we could do, because we're going to do it. So, all right, we're getting near the end. Our last layer, integral of 12y, well, that's going to make 6y squared. Then minus 8 thirds y cubed, and plus 1/3 y to the 4th, right? Here, you divide by 3, because you're going to add 1, divide. Here, you're going to divide by 4. At 3 plus 1 is 4. Divide by 4. That's how the 4 became a 1. And we're going to evaluate from 0 up to 3. Well, we plug in 0, you get 0. That's good news. So we get, plug in 3. 6 times 9. That's 54. Here, we have a 3 downstairs. There's a bunch of 3's upstairs. So we cancel off one of the 3's, so we still have 2 3's upstairs, making this 8 times 9, or 72. Last one, 3 to the 4th, but there's a 3 downstairs, right? So it's really like a 3 cubed, or 27. Now, if you take 54 and you add 27, you get 81. And if you take 81 and you subtract 72, you get 9. Now, you might be saying, 9 what? We don't know. They didn't give us units. So it's 9 of whatever you're using to measure mass. All right. Now, at this point, you're probably thinking like, cool. Can I do this? Yes, you can. I know this looks daunting, but believe me, this is my 3rd time attempting the problem. And so by my 3rd time, I got really good at it. That's why you attempt these things, right? You try. You make mistakes. You say, oh, how can I make it better? And oftentimes you say, look, try to make good choices at the beginning so that you can be successful in the end. That's good advice for calculus, for schooling, for life. Make good choices at the beginning so you can be successful in the end. And we want you to be successful, and you can succeed. I know I, for one, am happy to have finished this problem, because that means we get to keep moving on. All right, let's go for it. Number 6, integrate the function f of xy log of x squared plus y squared to the 5/2 over x squared plus y squared over the region R 1 less than or equal to x squared plus y squared less than or equal to 16. Now, as we look at this problem, we say, whoever wrote this problem really loved x squared plus y squareds. And but what is it telling us? Well, when you see x squared plus y squared, you say, hey, wait a second, that should ring a bell. We know that x squared plus y squared equals r squared. So this is kind of trying to signal to you that you should be thinking of polar. And all right, so we're going to think polar. But it's not the only thing. Think about r. r involves x squared plus y squared. And what is that? Well, you have circles. You have the inner circle, x squared plus y squared equals 1. That's the circle of radius 1. Okay, that's your inner bound. Your outer bound, x squared plus y squared equals 16. That's a circle of radius 4. Not 16, but 4, right? X squared plus y squared equals r squared. Let me make it a little bit bigger here. All right, so we're going to go out to 4. All right. Well, they're not perfect circles, but that's okay. We understand. We're amongst friends. And what's our region? Well, it's everything between those two. So our region is sort of a flat donut. If we wanted to be very fancy sounding, we could say, oh, it's an annulus? Yes. But that's just a way of saying flat donut. All right. So there we go. There's our shape. And maybe I'll choose a different color just to really emphasize the region. So, right, 1 and 4. All right. So with that in mind, we say perfect. So we're going to set this problem up in polar. So we need to think about how do we change the function? Well, we say anywhere you see an x squared plus y squared, you put r squared. So this becomes log of x squared plus y squared is r squared to the power 5 halves over x squared plus y squared is r squared. Now, we're going to take advantage here. R squared to the 5 halves power, that's log r to the 5th over r squared. But we know stuff about logs. We can say, hey, see this exponent? We can pull it down. And so we do that. And that becomes 5 log r over r squared. All right, so that's one thing, our function. We'll make a note, note number 2, our dA, how we're breaking things up. Well, in polar, that's r dr d theta. Okay, so don't forget the r. It's going to be very important. Sometimes it's critical to the point that without it, hopeless. With it, hope. And we like to be hopeful people. We have a lot to hope for. Now, we have to describe our region. So, always remember, polar comes from the origin. It's the pole. So, where do we go from? Well, the answer is we go full circle. Perfect symmetry. So our region, in terms of theta, we go 0 up to 2 pi. All the way around. Now, where does r go from? Well, we start at the inner part, head out to the outer part, from the origin. So, what's the inner part? The circle, r, and x squared plus y squared equals 1 becomes r equals 1. The outer part, r equals 4. So, let's put this all together. Putting it all together, what do we have? Well, we have the integral, our function 5 log r over r squared, r dr d theta, theta 0 to 2 pi, r 1 to 4. And we can cancel off one of our r's. Pew, pew. There we go. You don't have to make the pew sound, but doesn't it feel good? We say, okay, well, let's think about this. We're integrating. We have a log of r over r. We say, idea. If you take u equals log r, du is 1 over r dr. So this becomes 0 to 2 pi. Haven't done anything on the outer layer. And then we get 5 stays as 5, u, and then dr over r becomes du. So we have an integral of 5u du. Now, where do we go from? Well, plug in log of 1, 0, log of 4, log of 4. So this is log of 1 equals 0. And we say, okay, well, that's the integral we can do. So that makes us 5 halves u squared from u equals 0 to u equals log 4. You don't have to go back to r's. When you have definite integrals, always move forward. And we have our d theta. And we say, okay, well, that becomes integral 0 to 2 pi. When you plug in 0, you're going to get 0. Plug in the top part, you get 5 halves log of 4 quantity squared. Okay, but we're integrating that with respect to theta, but it's a constant. Crazy looking constant, sure, but constant nonetheless. So log of 4 quantity squared. And I want you to be careful because you're probably thinking like, oh, hey, we pulled down the 5 before. How about we pull down the 2? Because we can't. All right, why can't we? This 5 was inside the log. This square outside the log. So be careful. Be careful. Now, there's a theta. Theta equals 0. Theta equals 2 pi. And you plug in 0, you get 0. Plug in 2 pi, and you get 2 pi times 5 halves. Well, the 2's cancel, so you end up with 5 pi log of 4 quantity squared. Compared to some of the other problems, this one, highly desirable. We like this one. All right, good. Okay, let's keep going. Number 7, rewrite the integral, this integral, in the order dy, dz, dx. So this is a change the order of integration problem. We don't have to integrate. Whew. So this should hopefully not be so bad. All right, so let's start by figuring out what's going on. We need to grab our current description from our bounds, use that to figure out our shape, and then use that to go to our new description and our new bounds. So, just as a reminder, we pair things up. So we have our z and our x and our y. Okay, so we should pair things up. This is when I would be nice to have more space sometime on some of these problems, but imagine we planned ahead. Okay, so let's start by our outermost layer, -2 less than or equal to y less than or equal to +2. Okay, that's not so bad. I think we can make progress with that one. And then if we go to our next layer, we have our x. And x says go from y squared up to 4. All right, and then we have our z. And our z says, oh, go from 0 up to 4 minus x. All right, so those are all of our pieces. And, well, we got to start figuring out how do we put this all together? What does it all mean? I like to work up. So I'm going to sort of think about y. Y doesn't take me very long to think about. I'm going from -2 to +2. And so I'll pretty much jump right to y and x together. So let's focus on y and x together. Okay. So we have x, we have y. We're going from -2 to +2. So -2, +2, and we're going in between. Now let's talk about x. So for x, we have two curves. We have the curve x equals 4, which I'll mark here. And then we have the curve x equals y squared. What does x equal y squared look like? It looks like a parabola, but we're going to turn it, right? So imagine I was flexible. So we're turning it on its side. And so it's going to do the following. And you might notice something very convenient. When y equals 2, 2 squared is 4, and 4. So this actually here, this is at the point 4 comma 2. And negative 2 squared is also 4. This point here is at the point 4 comma negative 2. Now, it says we go from y squared on the left to 4 on the right, right? Low to high. So if you pick a y value, we start at the y squared and go to 4. So the shape, our region, is that portion there. All right, so that is what's going on in terms of the xy portion, the outer two layers. So let's bring it up now to the third dimension, 3D. No glasses required. Okay, so we'll do some sketching here. And we have our x, y, z. All right. Oh, this will be interesting. X, y, z. Now, this part here, it's going to come and slide to there. Right, just turn it, move it over. If I had a better special effects budget, there'd be some cool animation. You'd be like, whoa, that's so cool. I don't have that. But we have this shape here. And so we have this is going on. Here is our shape. There's this x equals 4 piece here. Here's this x equals y squared piece over here. And we'll go ahead and shade it in. All right, so that's our part downstairs. Now, where are we going from? Well, we're starting at z equals 0. Now, z equals 0 also code for xy plane. And that's perfect. This is sitting in the xy plane. So this is actually the bottom of our shape. We found the bottom. Woohoo! Nice! So this is our z equals 0. Okay, up to where? Well, up to 4 minus x. Now you might be saying, wait, what is 4 minus x? Okay, so we know what z equals 0 looks like. We can go ahead and we'll sketch it one more time. So for z equals 0, this is the xy plane. And so you sketch the xy plane. Now, for z equals 4 minus x, you might say, wait a second, how is that three-dimensional? You're missing the y. Ah, good catch. Well, what's going to happen is the following. Imagine you're here in the xz plane. 4 minus x does look like a line, but now you copy it in the y direction. So it's a plane, but now you sort of tilt it up. And where does it hit? The z-axis. It hits the z-axis here at 4. So this is x equals 4. We're hitting this, sorry, not the z-axis, excuse me. Where are we hitting the xy plane? Well, along this x equals 4. And then we hit the z-axis at positive 4. So what does this look like? Well, it's flat. And so we have this, we're going up to that. Okay, so we're going to go down. So here we have this flat shape. This is our plane, z equals x minus 4. And last thing to add into our picture before we start switching gears is to say what's going on. Well, we're going from z equals 0 up to z equals x minus 4. So we are just going straight up, right? So we're going straight up, including on this boundary. So ultimately, there are 3 bounding surfaces, and that's important to know. We've actually written them down. One of them is z equals 0. One of them is z equals x minus 4, right? The flat at the bottom, flat slanted face. And then there's this sort of wrapping around part. What's the wrap around part? X equals y squared. So those are the 3 surfaces that drive everything else that we're going to be doing. All right. Whew. Good. Yeah. How you doing? You doing good? That's great. Because now we need to change our order. Okay, so we have our shape. So let's think about how we find our order. We're going to go in the order dy, dz, dx. So when I think about setting up the order, I go through 2 layers. The inner part, have our inner dialogue, and really this, for me, we're identifying surfaces. Now, what's going on? Well, I say I'm going to be integrating, and the inner part is going to be an integral with respect to y. So I don't have to worry about the x and z. I'm just focusing just on y. What's happening with respect to y? Now, I come back and I say I have my solid. What is the y direction? Can I identify that? Well, yes. The y direction is going to be moving parallel to the y-axis. So this is the y direction. And I say, okay, I'm moving back and forth. So I think of being in the solid. I'm in the solid and I move back and forth. What am I hitting? Well, the answer is I'm hitting the wraparound part, right? I come from one side of the wraparound to the other side of the wraparound. So I'm sort of bouncing back and forth between the 2 parts that wrap around. So I hit on the left, I hit the x equals y squared. On the right, I hit the x equals y squared. And you're like, oh, that can't be right. Well, no, it's not, because we haven't solved it for y as a function of x. So if x equals y squared, what is y? Y is plus or minus square root of x. Oh, plus minus, 2 things. So the positive y, that's to the right-hand side. The negative y is to the left. So that becomes y is minus square root of x. And here we get y is positive square root of x. So minus root x to plus root x. All right. So that's the inner part. Now, let's do the outer part. Okay, so for the outer part, we're going to look down the axis. So look down, in our case, y, and see the shadow. Right? What does it look like as a 2-dimensional thing? So we're going to have an integral, stuff, and then we're going to be doing our dz dx. Okay, so we should draw a picture here. So we're looking down y. So you have to imagine we're little tiny people standing here, and we're looking down the y-axis. Our vision says, look down y. What do we see? What do we see? Well, what's happening is the slanted side basically disappears, right? And we don't see any of that wrapping. We see this flat thing here that's going in the xz direction, because as we look down y, we're only going to see xz. So we see this flat surface here. When we look at it from the edge, becomes this line. And then this part that's wrapping around becomes the triangle. So this is what we're seeing when we look down the axis. And we say to ourselves, okay, do we know anything? Well, yeah, we hit at 4 and at 4 again. We say, this will be good. This will make things pretty straightforward. I say, okay, so we can start with our outer part. X, where does X go from? Low value of X to high value of X. And the answer is low value is 0, high value is 4. 0 to 4. Where does Z go from? Well, pick a value of X in the middle and think about what happens to Z. Where do we go? Up, down. Well, we start down here. This is the line Z equals 0. So we say, okay, we start at 0. That's the low value. We go up to the high value, which is here. And this is Z equals minus X, because slope is minus 1, plus 4. So, or 4 minus X. So we're going to go from 0 up to 4 minus X. That's our outer two layers. And now we can put it all together, and we say, all right, our integral is going to be 0 to 4, 0 to 4 minus X, minus root X to plus root X of dy, dz, dx. And that's the answer. Woohoo! These are fun problems. Now, they're fun once you get the hang of saying, hey, what do the shapes look like? Until then, they're like, but hang in there. You can do it. We believe in you. All right, let's keep going. Number 8. Find the volume of the solid bounded by the surfaces x squared equals 2z, y plus 2z equals 4, and y equals 0. Okay, so what do we do? Probably one thing we should do is figure out what this looks like. And so we have 3 surfaces, right? And so I think we should understand each one of them. Let's start there. Y equals 0. That one's probably the easiest one. And so we'll start easy. We can do that. What does y equals 0 look like? Well, y equals 0 has another name, and that is the xz plane. So we say, aha, that we know what to sketch. That's the xz plane. Okay. So we'll make a note underneath it, just so you don't say, well, it's this floating rectangle, xz plane. Okay, so that's okay. That's not so bad. We got that down. All right. Well, let's try another one. Y plus 2z equals 4. Let's try to see what that would be. Again, we have our x, y, z. And you might say, well, wait a second. There's no x. That's okay. Start by drawing it into y and z. Y plus 2z equals 4. Well, it would hit if it was just in the yz plane, it would hit y at 4, z at 2. It'd be a line. But now, you say just copy that in the x direction. So what you get is it's a plane, but it's been slanted, right? Turned on its side. And so y plus 2z equals 4. That's this sort of sideways plane. All right. Well, good. And last one. X squared equals 2z. Okay. What is that one? Interesting. Okay. We should make some notes here. This is our y plus 2z equals 4. Okay, x squared equals 2z. All right. Well, again, you're thinking, wait a second, there's no y. That's great. What can we do? Well, we can solve. Say, look, that's like z equals a half x squared. So that's like a parabola in the xz plane. And now you just copy that back and forth. So what you're getting is you're getting this trough that just goes along. All right. So it's like you folded a piece of paper into a trough shape. All right. So there you go. Okay. So there we have our three shapes. And now we sort of say, okay, how do we put these all together? That's actually a good question. And, well, that's why we're here, right? To answer good questions. And as we start answering them, we start thinking like, okay, well, what can we do? You may remember there used to be these things where if you cross your eyes and all of a sudden a picture would emerge. Imagine you had three eyes and just put them all together. Well, we're looking for something that we can pull out that's bounded, and we don't want anything that shape that goes off forever, because every surface is basically cutting our space up into pieces, and so there's multiple pieces that we have here, but we want the one that's finite. And as we look at it, we say, oh, what we can do is we can imagine we'll take the xz plane and take everything where y is positive. We'll take this y plus 2z equals 4, slice it down, and then we'll be above this trough. So like we want to be to the right, below, and above. Those are that combination, right? That's the combination of those three, which makes things finite. So, all right, let me catch up. I forgot to write down z equals a half x squared. So let's put this all together and say, what do we really have here? All right. So I said we want to be to the right, below, and above. And mark this here. We want to be right, below, and above. So if we put this all together, we have a couple of things going on. This y plus 2z equals 4. We have a piece that will come along here. And then it's going to come down. We have, I'm looking at what happens here just in the xz plane. So in the xz plane, this part right here is sitting here nicely at z equals 2. At z equals 2, you have x squared equals 4, and we get this shape here. All right, so this, in the xz plane, this is at positive 2. Here we're at negative 2, and this is also at 2. So that's where we're hitting the xz plane. That's not a bad place to start, by the way. It's just look at the intersection. What does this and that intersect look like? Well, it looks like a line. And then you can say, well, what does this and this intersecting look like? Well, it looks like this parabola here. And then you can say, okay, so what does this and this look like? Well, that's the fun one. Well, what's going to happen? Well, we're going to come down and we're going to hit here at 4. And so we're coming down and then coming back up. And so we have our shape here. So I'm essentially have marked 3 curves. Those 3 curves are the intersection of these 3 surfaces. And so finally we put it all together and we say, all right, so we have on the back side the xz plane, that's this piece back here. The top side, that's our y plus 2z equals 4. That's this part right here. But then we have this piece, the trough. And the trough, it's not the easiest to see, but it's still there. It's still floating around, right? So it's we're going through. So that's our basic shape. All right. All right. Interesting. Interesting. So, how do we find the shape? No, it's nothing so complicated. The hard part is getting a picture. Once you have a picture, you say, well, if I want to find volume, I can do the following. I can integrate 1. And like, yeah, that's totally true. That's how you find volume. And so what's the work? Well, the work is set up the bounds. Like, yep, that sounds like work. And you think about the shape and you say, okay, well, I have choices, right? There's multiple ways we could set this up. Now, some ways make more sense than others. The question is, do we want to move surfaces up, down? Front, back, side, side? Any one of them would work. Now, looking at this, I feel most comfortable with this part right here being my outer layer. So, with that in mind, here's my thought. I'm going to set this up as an integral of 1, and I'm going to go out I should be careful here. My outer layers are going to be in the xz plane, so my inner part between surfaces is with respect to y. So I'm going to do dy, dz, dx. Then I just have to actually set these bounds up and integrate. Okay, so let's do the inner part. By this point, we're pros. So we're doing something where we're integrating with respect to y. So the y direction, that's a left-right motion. Left, right. What are we going to between? What are our surfaces? Well, it's one of these 3, right? 2 of these 3. One of the surface will be this one. That's our left-hand surface. That's the back side. The other surface is going to be this one. And so we're going from y equals 0 on the left, and we're going to go to y plus 2z equals 4 on the right. In some sense, you can see the fact that y does not show up here is a good clue. You can't really use that for your surface for y, because you can't write as a y equals if there's no y to begin with. So we say, okay, that tells us 0 less than or equal to y, and then here, solving for y, 4 minus 2z. So 0 up to 4 minus 2z. And we can go ahead and put it in up here as well. All right, that's the inner layer. Now the outer layer. For the outer layer, what do we have? Well, we're going to have integral, stuff, dz dx. We're going to look down the y-axis. As we look down the y-axis, what are we going to see? Well, we see, namely, just x and z. And we see the parabola. And we've mentioned before, this is at -2. This is at +2. And we say, well, where does x go from? -2 to +2. Okay, that's good that we've already mentioned it. And then you say, okay, well, where does y go? Sorry, where does z go from? I should mark this. This is the xz plane. And where does z go from? Well, you pick an x somewhere between -2 and 2. And you say, well, we go from the parabola up to that line. Then the line at the top, that's our z equals 2. The parabola at the bottom, that's our z equals 1/2 x squared. So we're going to go from 1/2 x squared up to 2. And those are going to give us our outer two layers, -2 to 2, 1/2 x squared up to 2. And we're off to the races. Okay, so we're ready to integrate. Integrate with respect to y. 1, that's not so bad. That's going to be just y. And evaluate from y equals 0 to y equals 4 minus 2z. All right, well, that becomes integral -2 to 2 of integral 1/2 x squared to 2 of 4 minus 2z dz dx. Well, that becomes integral -2 to 2 of 4z minus z squared. And you evaluate from z equals 1/2 x squared to z equals 2. When you plug in 2, you get 8 minus 4, right? 4 times 2 minus 2 squared. So that becomes 4 minus 4 times 1/2 x squared. So that's going to become 2x squared. And then minus minus makes a plus. Then you have x squared, which is 1/2 x squared, squared, right? So 1/2 x squared would make it 1/4 x to the 4th. All right, dx. So to be clear, this 4 came from plugging in 2, 8 minus 4. This minus 2x squared comes from 4 times 1/2 x squared, but we subtract. And this 1/4 x to the 4th comes from 1/2 x squared squared. Normally there's a subtract, but we're subtracting that. Okay, so that's what we're up to. Now we have to integrate this. And we say, okay, well, we have almost enough. We see some real estate up here, so we'll finish the problem upstairs. But first, let's integrate. That's going to be 4x. Actually, you know what? Let's go ahead and take advantage of something while we're here. Notice you have an even function. All the exponents are even from -2 to +2. You can use symmetry here to cut the integral in half and say, like, hey, you know, the part from 0 to 2 matches the part from 0 to -2. So you can double the integral 0 to 2 of 4 minus 2x squared plus 1/4 x to the 4th. Why do we like that? Well, because it brings in a 0. 0's a friend. All right. So, from below, so we know where we're coming from. This will equal what? Equals, we have 2. We have 4x minus 2/3 x cubed. And then plus 1/20. Whew, my goodness. X to the 5th. Evaluate 0 to 2. All right. All right, we've got it all on the screen. Good. Whew. Now when you plug in 0, you get 0. So we're in the home stretch. That's 2. 4 times 2 is 8. Minus, well, that'll be 8. All right, 2 cubed is 8. Times 2, 16/3. Now 2 to the 5th is 32. But we're going to take advantage. We have a 20 there. 20 is 4 times 5. So that knocks out 2 of our 2's. Okay, so just so I don't lose track of the story, I think this has 1/4 times 5. And 2 to the 5th, that's 4 times 8. So we have a plus 8/5. And now we say, okay, well, that's good news. I'm going to go ahead and pull out an 8 for a second here. That's 16 times 1 minus 2/3 plus 1/5. And get a common denominator. So that's 16 times 15/15 minus 10/15 plus 3 over 15. And if we do that, well, 15 minus 10 is 5. Add 3 makes 8. 16 times 8 gives us 128. So answer 128 over 15, and that's the volume. All right, now recap. What happened here? Well, we said, look, we're going to find our volume. First, we describe our shape. We figure out how our shape sets up. We integrate 1 dV, pick an order, and then off we go. Could we have picked different orders? Yes. Would we get the same volume? Yes. Is this one necessarily the best? I don't know. I just picked one. There's lots of ones that you could have picked. I just picked one because I felt like this one would be relatively easy to describe. And that's a good strategy. You know, remember, we want to be nice to ourselves. And we deserve it. We're good people. Good, hardworking, calculus people. So do what you can to be nice to yourself. All right, let's keep moving. Number 9, consider a thin plate covering the planar region. Oh, by the way, thin plate, you'll sometimes see the word lamina. So if you see a lamina, thin plate. X is greater than or equal to 0, y greater than or equal to 0, and x plus y less than or equal to 1. Whew. Okay, after all these shapes, it's so nice to come back to something that feels comfortable. X greater than or equal to 0, y greater than or equal to 0, x plus y less than or equal to 1, well, that is a line, and it goes through x equals 1, y equals 1, which means that our thin plate is a triangle. Hello, triangle. You look marvelous. Now, the density of the plate is given by this expression, 10y plus alpha. Find the value of alpha so that I sub y equals 3. And, okay, so we have a density. We have this, I sub y. Let's talk about what that is. So I is inertia. So this is inertia. And then the sub y means with respect to the y-axis. So what's the generic formula for inertia? So the generic formula is the inertia of something. We'll go ahead and say y. It's the integral, and we're a two-dimensional integral, so we'll go ahead and write it as a two-dimensional integral. Integral over our region of, we have our distance squared, density, and dA. In the formula sheet, it says measure here, because that says, are you 1D, 2D, 3D? We're 2D, so dA. So density dA is mass. Mass times distance squared is inertia. Okay, so we're going to be careful here. When we talk about distance squared, it's distance with respect to something. Distance is not quite the right word. A better word is location. But we'll start with distance. So this here, that's going to say distance with respect to, and now I know I made that harder to read, with respect to y. So you might say, aha, so that means we're going to put in a y there, yes? No. No. So this says, whoops, I want to change colors here. So with respect to the y-axis, so distance is x. Think of what's going on in 2D. If I have x comma y, how far am I from the y-axis? Well, it's your x far away. X is how far out you go. And so you say, oh, okay. Well, great. So we're ready to put most of our pieces together. So we can say we have that our inertia is 3. That's I sub y equals integral. The distance squared becomes x squared. Then we have our 10y plus alpha. And then we have to choose dy or dx. Do you want to integrate with respect to x first or with respect to y first? Well, this comes back to what we said in a previous problem. Which one would we rather delay integrating? Because I see x squared and here I see y, I look at this and say, I would rather do the y first, delay my integrating of x if possible. And we say, all right, we'll do that. We're down with that. And we say, okay, well, let's look at our bounds. Where does x go from? Well, we look at our picture. We say, well, the smallest value for x is 0 and the largest value is 1. So 0 less than or equal to x less than or equal to 1. All right, there goes our x bounds. Where does y go from? Well, we can imagine we pick a value for x, and then we say, okay, where are we running from? What curves? Well, the bottom part, that's the line y equals 0. The top part, that's the line y equals 1 minus x. Right? Y-intercept of 1, slope of minus 1. So we're going to go from 0 up to 1 minus x. All right. Well, let's do it. So what do we get? This becomes the integral from 0 to 1. We're integrating with respect to y, so we have, if we multiply this through, we'll have 10x squared y squared over 2. So that's going to become 5x squared y squared plus alpha x squared y. Okay, so that's distribute, integrate. Evaluate that from y equals 0 to y equals 1 minus x. And then we're going to integrate that with respect to x. All right. It's okay to take a second, make sure you didn't miss a silly thing. And because that happens a lot. I know I sometimes do that. Okay, so that becomes integral 0 to 1. Good news, if you plug in 0, you get 0. You should always check. Sometimes you don't. So always, don't just assume it's always 0. But it frequently is, which is why we like 0. Plug in y equals 1 minus x, we get 5x squared times 1 minus x quantity squared plus alpha x squared times 1 minus x. Okay, and we're going to integrate that dx. Well, let's expand. So here, 1 minus x quantity squared, that's 1 minus 2x plus x squared. So if you distribute the 5x squared through, this becomes integral 0 to 1 of 5x squared minus 10x cubed plus 5x to the 4th. Okay, that's the first term. Now this alpha x squared we also distribute, plus alpha x squared minus alpha x cubed. All right. And now I'm not going to combine these just because I don't know alpha, so I'll just keep those separate for now. Okay, so integrate patiently. We get 5/3 x cubed. Here we'll get minus 10 over 4 x to the 4th. Well, that becomes 10 over 4 becomes 5 over 2 x 4, right? Divided by 4? Yes, 5 over 2. Then we get 5 over 5 x to the 5th. Well, we can just think of as 1 x to the 5th. Then we get alpha x cubed over 3. So plus alpha over 3 x cubed. And then here, minus alpha x4 over 4. So minus alpha over 4 x to 4. And we're going to evaluate that from 0 to 1. Now, good news. Again, plug in 0, you get zeros. So we plug in the 1s. So that gives us 5/3 minus 5/2 plus 1 plus alpha over 3 minus alpha over 4. Okay, so let's start with this first group, the ones without the alphas. And that's common denominator would be 6, so that's 10 over 6 minus 15 over 6 plus 6 over 6. Or that's 16 minus 15 over 6, which is 1 over 6. Here, we can pull out the alpha. We get 1/3 minus 1/4. Common denominator would be 12. So that's alpha 4 over 12 minus 3 over 12. Or that's 1/12 alpha. All right, so where are we at? Let's remember, we have an inertia of 3. So we have gone to the following point. Namely, we now know that 3 is equal to 1 over 6 plus 1 over 12 times alpha. I don't like fractions, so I'm going to multiply everything by 12. 36 is equal to 2 plus alpha. Right? Just multiply everything by 12. Or alpha is 34. And there you go. What a number, right? Yeah, it's definitely not what you would have thought. And but that's okay. It's not necessarily what we think. It's what does the process tell us. Work through the process. And that'll help you figure it out. All right. We're doing great. Let's keep going. Number 10. Evaluate this integral over a region y over x squared plus y squared cubed dA, where the region is what? Well, it's a set of points such that, that's what this notation means. So if you see squiggly lines, collections, points such that, all right, x is greater than or equal to 0, y is greater than or equal to 0, and x squared plus y squared is greater than or equal to 4. Now you might say, wait, what? Hold on. Let me try to understand that. So some of this is pretty straightforward. X greater than or equal to 0 means this. Y greater than or equal to 0 means that. Now what about x squared plus y squared greater than or equal to 4? Well, x squared plus y squared equals 4. That we can get a handle on. That's the circle of radius 2. Now what do we want? We want to be bigger than that. And yet first glance you're like, wait, what? That means we just keep going forever? Yes, it's possible, right? So this is an integral where you have this huge infinite region. Now, does that mean we're done? We say, blows up. No, unfortunately, just because your region is infinite does not mean that the total is not finite, right? We don't know. We have to check. So we've got our work cut out for us. Okay, now there's some big clues. They've already been floating around, so let's not pretend like we haven't seen them. The x squared plus y squared in both the region and the function, we see that and we say to ourselves, hey, come on, you can't get this past me. X squared plus y squared equals r squared, and that means we're going to think polar. And when we think polar, there's more than just the x squared plus y squared equals r squared. we have x equals r cosine theta, and that y equals r sine theta. And we say, okay, so now we've got to do our three pieces, our due diligence, if you will. Every integral has three parts: the function, how you break things up, description of the region. The order you do it usually doesn't matter. So some parts are really quick. Like the dA, you say, well, wait a second. Polar, the way we break things up is you have r dr d theta. So you say, great. That was pretty straightforward. Now let's talk about our function. This y over x squared plus y squared cubed. What will it become? Well, y over x squared plus y squared cubed is going to become y r sine theta. X squared plus y squared is r squared cubed, r to the 6. So that becomes sine theta over r to the 5th. Now that's just for the function. That's separate from that r. We haven't taken that into account yet. Now, the last thing is our region, right? Okay, so what is that going to be? Well, we think of everything, of course, in relationship to the center. As you look at this, what angles are involved? Well, we're going to go from 0 to pi over 2. So 0 less than or equal to theta less than or equal to pi over 2. What about r? Well, once you pick a direction for theta, you come out, you say, where do you start? Where do you end? Well, the start, that's pretty easy. 2. Where do you end? You don't. You keep going. So we go all the way out to infinity. So if we were putting on our Calc 2 hat, we would call this an improper integral. But we're not going to be that formal here and just say, yeah, throw an infinity on. And the only time we're going to worry about it is if at the end we get something that's ambiguous, like, oh, what is this? When we have the ambiguity, then we really worry about limits. If we don't, we're like, cool, we love it. Let's go with it. All right, so now we have our pieces. Let's put it all together. So we get an integral, our function, sine theta over r to the 5th, r dr d theta. Theta goes 0 to pi over 2. R goes 2 to infinity. All right. This is the same as sine, integral, sine of theta. And instead of r over r to the 5th, I'll write this as r to negative 4. dr d theta. Now, I'm going to use something that we've mentioned in class, haven't really used much of, which is I can pull these integrals apart because the bounds are constants. There's no thetas or r's in the bounds. And the functions I can separate by multiplication. So I can pull this into two separate integrals and do each one of them by themselves. So we get, for the theta part, 0 to pi over 2, sine of theta d theta. And for the r part, integral 2 to infinity, r to the minus 4 dr. All right, let's start with the integral of sine. Integral of sine is negative cosine. Yeah, I know. I get thrown off by that one too. And we're going from 0 to pi over 2. When you plug in pi over 2, cosine of pi over 2 is 0. So you really get 0 subtract negative 1, which is 1. Okay, so this is 1. Good. How about here? Well, add 1, r to negative 3. Divide by that, so you get negative 1/3 r to the negative 3. Evaluate 2 to infinity. Now, when you plug in infinity, plug in. Technically, this is where well, what does it mean? It's like, okay, if r is really big, the r negative 3 is really small. So if you think of r heading to infinity, you get something heading to 0. So plugging in infinity gives us 0. Minus, and here we have minus 1/3 times 2 to negative 3, which is 1 over 8. Minus minus makes a plus, and so this part gives us 1 over 24. Multiply those together, and we get our final answer, 1 over 24. And that's it, our final problem. Oh my gosh, wow. It's been a while since we've done one of these quizzes, right? But this one feels like we've kicked it up a notch. Well, that's because integration really pushes us in thinking geometrically. And it takes time. I'm not going to pretend like it doesn't. And if you're picking up quick, I'm so happy for you. And if it's taking you time, that's fine. Keep at it. You can do this. You're an amazing person. And I'm appreciative that you're putting in the time and effort to learn these skills, these tools, these techniques. It will pay off. Learning to think is such a great thing, and it's worth the investment, and you're worth it. Thank you so much for joining me. Hope you have a great day, and I hope you do well on this quiz and all the future quizzes we might do together. All right, I'll see you again. Bye.